Hi everyone, welcome back to PW International Boards. Friends, in this class, we are going to complete another chapter, that is energy, work and power for your physics Cambridge IGCSE exams. In this class, we are going to first talk about the most important theoretical concepts, and after that, we are going to also solve some of the past year problems from these topics, right? So without any delay, let's start our class. But before that, let me tell you, we are going to follow a different strategy to start this chapter, because I know usually when you're going to follow this chapter in your textbook, this chapter is being started from energy. They talk about energy, then they talk about work, and followed by they talk about power, right? But what we are going to do is we are going to first talk about work, then we are going to talk about energy, and then followed by that we are going to talk about types of energy, conservation of energy, and then power and efficiency. Why we are going to do that, I'm going to explain it why we are learning the chapter, right? So let's start today's class with discussing what do we really mean by work. First of all, when we are going to talk about work, we are going to say something like a work is done by a force, right? So whenever whenever you are trying to calculate a work, you are basically trying to calculate a work done by a force. Now we can define it. Work done by a force can be defined. Work done by a force can be defined as it is the product of force and displacement. Or you can read something like work is performed when a force causes displacement of a body over a certain distance in the direction of force applied. What do you mean by this? Let's understand this with the help of an example. Let's suppose that we have got a body and it is kept on a surface something like this, and this is basically a box, right? And using a rope we are pulling this block in this direction. So let's say this is a force F, and because of this force F the body gets displaced, right? So there is a displacement of the body, and let's suppose the displacement of the body is something like this. So up to a displacement of x the body gets displaced. So I'm going to I was saying that work done can be defined as force times displacement, and displacement must be in the direction of force. So this is very important, that this definition, that the displacement that we are talking about, it must be in the direction of force. So this means that we will have to actually derive a general formula for work done, and I'll help you for that. Let's suppose instead of a diagram like this, we are making a diagram something like this. We have got a surface, we have got a box kept on this surface, and let's suppose a child is trying to pull this block using a rope, but now the child is actually pulling the block at an angle. So the force that is now acting is at an angle, so something like this. So this is the direction in which the force is acting, and I'm going to just draw a dotted line. This basically shows that uh, this is a line parallel to horizontal plane, right? And let's also draw a vertical line something like this, right? And let's suppose the angle made by this force is theta with respect to the horizontal line. Now I know that this is not in your course, you also don't have to worry about, but this is going to make your concepts more clear about work done, right? What we are going to now say is that this force has got two components, and those two components are, one component is acting in the y direction, one of the component is acting in the x direction. And you can also assume that the displacement of this box is going to be pretty much in the direction of x. And let's suppose that displacement is x. Let's just assume the displacement to be x. So now I'm going to write, in this case I'm going to write the work done as force, but instead of writing just as F, I'm going to actually talk about Fx, which is nothing but the horizontal component of force. Because if you are going to ask me in which direction the box is getting displaced, so it is getting displaced in the horizontal direction. So let's write down the Fx times the displacement, that is x, or you can just take another variable just for so that we don't confuse. So let's say this is d. So Fx times d. So now this is your work done. So this is now very important that we must find out the work done. When we are going to talk about work done, we must find out the force and displacement, the product of force and displacement. But we need to keep one thing in mind, that displacement must be in the direction of force, right? So for example, let's take another example. We are going to say that we have got a box and we have got a child who is actually trying to hold the box, something like this. So we have got a child and the child is trying to hold the box above his head in such a way, right? And the boy is actually moving in forward direction. So if the boy is trying to hold the box above his head, that means the boy is actually trying to apply the force in this direction, isn't it? That's how he is going to hold the box, and the displacement is in the forward direction. So in this case, I'm going to say there is no work done by this force. Why is that? Because force is acting in vertical direction and displacement is occurring in horizontal direction. So we are going to say there is no displacement in vertical direction and there is no force in the horizontal direction. So there is no work done by this force, right? You are going to ask me, so how does the box is actually, how does the boy is actually trying to move the box? That may be because of friction, that may be because of the muscular force of that boy, right? Work done by that force can be calculated, but not with the vertical force, right? Having said all of these things, now let's also talk about the some of the units, and we are going to also talk about whether work is a scalar quantity or vector quantity, right? So before this, whenever we talked about something like, let's suppose now we know what the formula of work is. So work is written as force times displacement, and displacement must be in the direction of force, right? So whenever we talk about a formula something like this, usually we used to say that force is a vector quantity, displacement is a vector quantity, so definitely work is also going to be a vector quantity. But that's not the case. Actually, work is a scalar quantity, and when you're going to move into some senior classes, you're going to see that work is actually written as the scalar product of two vector quantities, that is f dot s. Again, you don't have to worry about it right now. For now, you just have to remember that work is actually a scalar quantity. But I'm going to give you a little insight that how you can actually really imagine that work is a scalar quantity. Think about it, that when we are talking about work, we are saying that work is a product of force and displacement in the direction of force. So we are just dealing with two numbers, right? We are just dealing with two numbers. Let's suppose that Fx is actually equals to 10 and the displacement that happened was equals to 5 meters. If this was 10 Newton, this was 5 meters. So the answer that will come is 10 Newton times 5 meter. And finally, the answer is going to be 50 Newton meter. Now, I have got no interest in finding out in which direction the work is being done. There is no such concept that there is a direction of work done. The work done is 50 Newton meter. Now it could be, now we are not going to discuss direction, right? Because we have already talked about that displacement is in the direction of force. All right. So having said that, we are going to say that it is a scalar quantity. That means it just has got magnitude. It has got no direction. Second thing, its SI unit is going to be joules, which is a common name for Newton meter, that is denoted by capital J, right? Obviously, we have got some other units for this one as well. Like for example, is whenever you want to find out some another units like CGS unit is going to be, and I'm going to also explain the conversion, that we know that 1 Newton can be actually called as 1 dyne. That is the CGS unit for Newton, for force, times for displacement we are going to write it as centimeter. So dyne centimeter is basically something that we called as the CGS unit, which is also known as erg, right? And now we can find it out that 1 erg is actually equals to 10 to the power minus 5 Newton times 10 to the power minus 2 meters. This is basically 10 to the power minus 7 joules. So this is a unit that you must remember, right? Other than this, whenever we are going to, whenever a force is going to do some work, now there is a distinction between the what we usually use work in our day-to-day life, that we are going for work or we were doing some work, right? Whenever in physics we are going to talk about work, we are basically talking about a work done by a force because of which there was displacement of a body in the direction of force, right? So we must keep all of these things in mind. Other than that, we have covered everything about the work done. There's one more important thing, that work can be positive, it can be negative, or it can be zero. Now this is also sometimes a student gets confused when we talk about something like this, that how come work can be positive, negative, or zero when it is actually a scalar quantity, right? Usually we use plus or minus signs, or the sign, the positive or negative signs, just to show the direction. And when we talk about direction, we are basically talking about vector quantity. So this is another doubt that I'm just going to clear. When we are going to talk about work done by a force, and when we are going to discuss that work done can be positive, basically what we are trying to say is that the angle between force and displacement is an acute angle. Now, what do we really mean by this? We mean to say that something like this is happening, that there is an acute angle between force and the displacement. So then the work is going to be positive. If this angle becomes obtuse, then the work done is going to be zero. Then the work done is going to be negative. That means when the angle between the force and the displacement is greater than 90 degree, and if it is equals to 90 degree, that means we are talking about zero work done, which actually I just showed you, I just explained you with an example. Oh, can you see over here? This is the direction of displacement, this is the direction of force, there is a 90 degree of angle between them. So there is no work done, right? Although the you can also rewrite this formula as F into S cos theta. S is also displacement. In the last page I used a small d, so you don't have to worry it about, right? Moving on, after this, when we have already talked about work, now let's discuss some of the some of examples regarding this. Let's take an example. Let's suppose we have got a stone over here. You can consider it a stone. So if this is a stone, this should be a rope along which there is a force of tension, right? This is the direction of motion. Hopefully you are comfortable with circular motion. Can you please see that tension is always perpendicular to, or I should say centripetal force is always perpendicular to velocity, always perpendicular, no matter where you're going to talk, where you're going to talk about. Let's suppose you're talking about when the particle is somewhere over here, then the velocity is in this direction, and again the centripetal force, which in this case is tension, is always perpendicular to velocity. And we know that direction of velocity is exactly equals to the direction of displacement, because velocity is nothing but rate of change of displacement, right? So if a body is moving in east, it is also displacing in east. That's why we are saying that, right? So what we are trying to say is that the work done by centripetal force is always going to be zero, as I've just now told you that the whenever the angle between the force and the displacement is going to be 90 degree, the work done by that particular force is zero. So when you are going to talk about different cases, like for this one, I said that we have got a stone, right? So I was saying that a stone is in circular motion. stone in circular motion, or what I can say, I can talk about a satellite. Work done by gravitational force on a satellite is zero, right? So if a body is moving in circles, there must be a centripetal force acting on it. Centripetal force is provided by different forces, like in when a satellite is revolving around a planet, gravitational force is providing that necessary centripetal force. So it means the same thing. Work done by centripetal force is zero. Now in any which case, the centripetal force will be different. The work done by that different force is going to be zero, right? Having said that, now whenever you're going to actually do some work, what will happen? That work will actually get converted, and it will be stored in the body in form of energy. This is why we actually started our class with work and not with energy, because energy is ability of a body to do work. Now if I have not explained work to you, how are you going to understand what energy is, right? Now energies are of different types. There are many types of energy, and there are many classifications of energy. So we categorize energy into different classifications, right? For now, we have written it as energy is a property that must be transferred to a body to perform work or heat up that body. So this is just one sort of definition. Another type of definition can be, we can also write that energy is, it is the ability of a body to do work. Now I'm going to explain it in simple terms. Let's suppose that we have got a body something like this, right? And we have, when I say we, I mean to say that a force. Let's suppose that a force has done some work on it. So a force has done some work on it. Now this work will be stored in the body or the system in the form of energy. Now that energy can be anything. So I'm going to start with some of the most simple examples. Let's say, and we are going to talk about all of these energies in detail as well. Let's say that, let me use the same example. Let's suppose that we have got a body kept like this, and a force acts on it. Just figure out what will happen if a force is acting on it and it is displacing. It means that the velocity of the particle is increasing. The speed of the particle is increasing. Initially it was at rest, let's assume it for simplicity. That means after some time the particle will gain some speed. Is that correct? The particle will gain some speed. This means that the particle is into motion. This type of energy that is due to the motion, we call it as kinetic energy. So now the body has got kinetic energy. You might have, obviously you have heard it, but where does this kinetic energy have come from? It has come from the work done due to force. So work is converted into kinetic energy. Further, the kinetic energy can be converted into work as well. That's why we are writing that energy is ability of a body to do work, right? So although there are going to be different types of energy, but the main point is that its SI unit is going to remain same as work. That it will be also joules, because it is nothing. It is, the formulas are going to same. Everything will be same. It's just a new term, right? Whatever the work has been done by the force, now it is converted into a same quantity with a different name, that is energy. And energy are of different types. It could be sound energy, it could be light energy, it could be heat energy, it could be any energy, right? So we are going to talk about all of those types of energy. For now, if it is work, the SI unit will remain same. So will property, like it is also a scalar quantity. This will also remain same, right? So this is also a scalar quantity. Now moving on. Now we have got, like, see how many types of energy we have got. We have got kinetic energy, we have got gravitational energy, elastic energy, magnetic energy, electrostatic energy, chemical energy, nuclear energy, and thermal energy. So these are one of the most important types of energy. Among them also, you know that we are going to actually give more focus to kinetic energy and elastic energy and what we can say, we must also write potential energy, but what they have done is they have actually used potential energy over here. So it is gravitational potential energy, right? I'll write it over here, friends, for you. We have got gravitational potential energy. So that's why they have just written as gravitational energy. We have got elastic potential energy. So there is nothing like gravitational kinetic energy. Kinetic energy is just if a body is moving, that means it has got an energy which we call as kinetic energy, right? That's why the definition is moving objects have energy in their kinetic store. What do you mean by store? Store is just a way of putting things like the body has got energy. Now, in which store it has got energy? We are basically trying to say which type of energy is that, right? So gravitational potential energy, magnetic potential energy, electrostatics potential energy. That's why they are not talking about potential energy again and again, right? Nuclear energy, chemical energy, thermal energy. So the definitions are now, these things are very important because you know that in Cambridge IGCSE exams, some of the multiple choice questions, usually the paper 1 and paper 1 and paper 2, they sorry paper 1 and paper 1. So paper 1 basically in some many questions comes from topics like this, that a cycle was moving, what is the change in energy? So we have to tell what's the flow. So kinetic energy is changing into potential energy, or potential energy is changing into kinetic, and further it is getting changed into heat. So first we must remember the definition of these things. So kinetic energy is moving objects have energies in their kinetic store. I have already told you. Gravitational objects gain energy in their gravitational potential store. That's what I have told you, when they are lifted through a gravitational field. So we are going to talk about the gravitational and the kinetic energy in detail just after some time, right? So you don't have to worry about. So I've got notes for you, right? So please note them down. These are the different energies that we are going to look for. For now, let's move on to next one. Now we are going to talk about energy transfers. Now energy, that's what I was saying, that energy can be transferred from one form to another form, right? And it can be transferred into following pathways. Like first one can be mechanical, electrical, heating and radiation. Now why we are talking about mechanical as a whole? When we are talking about mechanical, basically mechanical energy means mechanical energy is nothing but it is the sum of kinetic energy and potential energy, right? So and then of course you know what electrical energy is. We are going to discuss is heating and radiation. So first one is mechanical energy. When a force acts on an object, like pulling, pushing, stretching, squashing, and there is a change in any of the kinetic store, like potential store or kinetic store. Electrical working is a charge is moving through a potential difference. That means there is a current flowing into the circuit. Now what will happen, that let's suppose that we have got a resistance something like this, and current is passing through it because there is some potential difference across this resistor. So what will happen, there will be heating effect due to electric current. So there could be heating effect. If this is a light bulb, then there can be light energy. So this is one of the pathway. Heating energy is transferred from an hotter object to a colder object, that is conduction. Whenever you touch a hotter object, the heat always flows from a hotter body to a colder body, right? Heating by radiation. So like for example is how come we actually get energy or heat from sun? Through electromagnetic waves, right? So that's the fourth point. Moving on, now let's talk about some of the examples, like potential energy is transferred to kinetic energy by mechanical working. Now I know that we haven't discussed potential energy or kinetic energy, but for now I'm going to give you the definitions of potential energy. So when we are going to talk about potential energy, although we have already discussed what do we mean by kinetic energy. So kinetic energy is energy possessed by the body, possessed by the body due to motion. So it's a quite simple and sweet definition, due to motion. So if a body is moving, it has got kinetic energy. That's, I mean, we can say it for sure. We can say it surely, right? For potential energy, we are going to say that if there is change in position or shape or size in the body, of the body, of the body, then we are going to talk about potential energy. Now, we can define potential energy in a broader way also when we are going to talk about conservative force, but since it is not in the course and we are right now preparing for exams, so I'm not going to divert from the topic. For now, just assume that, let's suppose that this is a body that is kept over here, right? Now I want to change its position. So if I'm going to change its position, something like this, I have done work. Now when I say I, what I basically mean is, let's say I'm talking something like this. This is the surface, this is the body, and there's weight acting downwards. That means there is a gravitational force acting downwards whose values is mg, right? So if you want to actually lift it up, you will have to apply an external force in this direction. So this external force will actually do the work. This external force will actually do the work, and if you're going to lift it up to a height h, the work done will be force times the displacement. And just to say to you, this force must be actually equals to mg. Now again, some of you might feel that there is a problem, because if these forces are exactly equal, how come it is going to actually ascend? What we are trying to do is, we are trying to lift this block with very small velocity. This should be very small, right? So that's why we are just keeping it exactly equal, and it's slightly, it's theoretical concept, so you'll have to understand it like that. And if you're going to lift it up to a height h, so the work done by the external force will be, the force is mg, the displacement is h, so the work done is mgh, and that's what the gravitational potential energy is. So this is not a formula of just potential energy, this is formula for gravitational potential energy. Well, there is a difference, because if you are going to ask me that what is the formula for potential energy, I'm going to just say that it is the product of force and displacement, right? If we can actually talk about potential energy, we can't talk about potential energy in every case. Like if you are going to move an object, something like this, let's suppose that we have got a surface over here, and we are moving an object along the surface. And if I'm going to just leave that over here, the object is not going to move in forward or backward direction, because right now we are talking about friction force. When objects move on a surface, we basically discuss friction force, and when you do work against friction force, that is not recoverable, right? So there is something that is called as conservative force or a non-conservative force. So there are only few forces against which, if a work is done, then only we are going to talk about potential energy. So for now, that's the only important thing that you will have to remember. And that's why when we were talking about different sorts of energy, we only discussed about gravitational potential energy, elastic potential energy, magnetic potential energy, and electrostatics potential energy, right? There is nothing as frictional potential energy, because there is no concept of frictional potential energy, right? Although again, I'm going to say that we are not going to go in that deep into those topics, because that's not part of the course. For now, we are going to just say that if we are talking about potential energy is transferred from kinetic energy by mechanical working, this basically means, let's suppose that we have got a surface something like this, and then we have got another surface something like this, and a body is moving. Let's suppose that a ball is moving in this direction with some speed v. So right now it has got some kinetic energy, and I'm going to choose this straight line as my reference line, meaning that I'm going to assume that the potential energy of this reference line is 0. So after some time, the ball will be somewhere over here, and let's suppose that it is at rest. So it has converted its kinetic energy into gravitational potential energy. So that's how the transfer happens, right? We can look for like different examples. Similarly, you can talk about thermal energy. Thermal energy stored in an electrical fire element is transferred by electromagnetic waves and by heating to the environment, like infrared rays, right? So when they are talking about electromagnetic waves, they are basically talking about infrared rays or infrared waves, right? Although every waves has got energy, it's not like just infrared, but if something is red hot, maximum amount of energy that's coming out of it is infrared. From sun also we talk about ultraviolet, infrared. These are the major portions along with the visible radiation. Then when we are going to talk about the chemical energy, when we are going to talk about the chemical energy, by the way, this one is actually stored in the muscles in the arm. It's transferred to elastic energy in the bow by mechanical working. So this is also a good example, right? Starting from chemical energy from your muscles, converting into the elastic energy, and then converting into kinetic energy, right? That is when they are saying mechanical, it will get converted into kinetic energy of the bow when it will be left. Now it is very important to understand that that's what we were talking about, that in your exams you are going to ask to fill the boxes. So the first box is going to be the chemical energy in your muscles. Second is going to be the elastic potential energy in the bow. In the bow. The third one is going to be the kinetic energy in the arrow. So that's how the flow is going to be, right? Moving on, after that, when we are going to talk about principle of conservation of energy, we basically mean to say that energy can't be destroyed or it can't be created for an isolated system, right? It will be conserved. The total amount of energy in a system is always conserved. That's what the principle of conservation of energy says. So for this for a better understanding, let's take an example. We have got over here as a diagram. In this initially we have taken chemical energy, which has got 100%. We are assuming that we have got 100%. Obviously when we are taking an amount, we are taking it as 100%. Now out of it, a small part of energy is being converted into the thermal energy transferred to surroundings, because we don't have I mean, because we can't have really 100% isolate, we can't have 100% of what we can say insulation. The energy will be dissipated in some form, and this is a word that we often use, that is dissipated. So dissipated basically means that the energy or the conversion of energy into a form which we never wanted to, right? Like for example, is we don't want thermal energy to transfer to surrounding, unless we are talking about a radiator or a device, something similar to that, right? But in this case, it is actually it is just a byproduct, a negative byproduct for this process. So that's why these things are known as dissipative energies, right? So this thing will be known as dissipative energy. After that, we have got thermal energy transferred to the surrounding again after some time. That means first it was gone to the boiler, then it has converted into steam, then it has converted into turbine, then the turbine will create the electricity. So this is nothing but a thermal power station diagram, right? First what happens, there is a boiler in which you have got water. It is heated up at high temperature, it is converted into steam. Steam is then thrown with high velocity at turbines. At turbines, due to electromagnetic induction, electricity is generated, and this is the process. So at every step, there is a dissipative energy. There is a energy that is being dissipated out of the system. But if you are going to add them, like if you are going to add this energy, if you are going to add this energy, if you are going to add this energy, and if you are going to add this energy, all should come out to be as 100%. This is what it is known as conservation of energy. But the useful energy that we have got is just 30%, which we can also call as is its efficiency. That the efficiency of this particular thermal power plant is only 30%. So if you are actually giving 100 joule of input as energy, that is 100% joule of chemical energy, the output of electrical energy is just 30 joules. The rest of 70 joules of energy was got dissipated into some or the other form, right? Having said that, let's move to the next topic. Now we are going to talk about, we have already discussed what do we really mean by potential energy, and when just to actually explain all over again, when we are going to talk about kinetic energy and potential energy. For kinetic energy, the formula for kinetic energy is half mv square, although you really don't have to worry about the derivation of this, but you can easily calculate it using the kinematics equation, and force equals to mass times acceleration. But for now, we are just going to talk about a simple thing, that if we have got a body of mass m and it is moving with speed v, then the kinetic energy is given as half times of mass times the square of speed. That's it. So this is the formula, and other than this, you don't have to worry about its SI units or anything like that, because again, this is its SI unit is also going to be joules, like every other energy. This is also going to be joules, denoted by capital J. It is also a scalar quantity, right? It is possessed by body due to motion of the object. We have already covered that. When we are going to talk about potential energy, now potential energy is of different types. Like for example, is we can talk about elastic potential energy. So when we are going to talk about elastic potential energy, its potential energy is half kx square, where k is the spring constant. So I'm going to also write it down for you, where k is the spring constant and x is the elongation in the spring, or elongated length, or compressed length. Similar to that, gravitational potential energy is given as ngh. So now it depends on different types of, usually you're just going to use these two ones, right, which are in your course. The SI unit is joules. It is also a scalar quantity like everything else, right? Every other quantity. After that, let's now move to the different types of energy. There can be like solar energy, there can be wind energy, hydroelectrical energy, geothermal energy, fossil fuels. That is basically your natural gases, and then nuclear energy and biomass energy. Now we are going to actually categorize all of these energy into, we are going to actually classify them on a certain basis, right? So now when we are going to actually classify them, we are going to say that let's classify them on the basis of their renewability, whether they are renewable or not. So there are two types of categories in this type of classification. First is renewable sources, second is non-renewable sources. For renewable sources, we are going to say these are those sources which are assumed to be abundant in nature and are sustainable. For example, as solar energy. Now although in theory and in reality, solar energy has also got a life, but that span of life is like it's too big for a humans, right, for human species. So we are going to consider solar energy as renewable. Geothermal energy basically means when we use the heat thermal energy of earth. Wind energy, biomass, hydropower, tidal, these types of energy, please remember their names, because these are going to be very important. The next one are non renewable energies. These are those which are found beneath the earth's surface and which are not sustainable. These are going to extend after some times, which are natural gas, coal, petroleum, nuclear energy, and hydrocarbon gas liquids. There is a point that is written that they are generally environmentally safe. Now this is not absolutely correct. When you're going to talk about, when you're going to compare like a hydropower and a nuclear energy, so again we can discuss about like different sorts of things, right? Like nuclear energy has also got some disadvantages, and hydropower has also got some disadvantages. But what I feel is that hydropower actually does more harm than nuclear power. The reason is that we know that to dispose the nuclear waste, it is actually quite difficult, but please remember that for making a hydropower plant, you have to actually reclaim a large amount of land, which was actually a part of a natural ecosystem. So that is also not that eco-friendly, right? So other than that, obviously natural gas, coal, petroleum, hydrocarbon, gas liquids, these are extremely extreme dangers to what we can say to environment. That's why we have said that generally the renewable energy sources are safe, right? So hopefully now you have got this concept. Now let's move on to the next topic. Now, when we are going to talk about energy consumptions, efficiency and power, we are going to first talk about what do we really mean by energy consumptions. So let's suppose that we have got an engine. In first case, let's suppose that we have got an engine, and in the second case we have got a resistor. So I'm giving you two examples. Let's suppose that in this one, whatever the input of this engine is, now what's going to be the input? So this is an engine, and the engine is basically running with the help of some petrol or some sort of an oil, right? In this case it is petrol. So because of this petrol, we are actually giving some energy into it. So this is that we call as input energy. Then there will be some dissipative energies that we don't have a control on, and after that we'll actually receive a useful output energy. A useful output energy, right? So we are going to say that if useful output energy is, let's say it is EO and input energy was EI. So we are going to write the formula of efficiency is the formula for efficiency is that useful output, or what, yes, output, E output divided by E input divided multiplied by 100. That's how you're going to find out the efficiency, right? Other than this, same thing you can consider it for a resistor. That means if let's suppose you have got an input energy EI coming in, and the useful energy is EO, again we are going to do the same thing for this one as well, right? Other than this, when we are going to talk about power, power is actually nothing but power is rate at which work is being done. Rate at which work is done, or now you know that we can also call work as energy. So now you can think it like this: rate at which energy is consumed or delivered. Or delivered. So I'm going to give you an example. Let's suppose this engine has a power of 500 or 5000 watt. This means that this engine consumes 5000 of joules of energy in 1 second. Or in some another example, let's suppose that we have got an electric bulb, something like this, and it has got a power of 40 watt. Again, this means that this consumes 40 joules of energy in 1 second, right? So now I think having said all of these things, now I think we can move to some questions. Let's see what are the questions that usually come in exams. So this is one of the recent exams, that is 2024. This is part of February March series, which is exclusive to India. Paper code is 12, obviously 0625. The question says, which row describes an advantage and a disadvantage of wind turbines? So for wind turbines, obviously the what we can say, the advantage is that we don't require any fuel. So that is actually a correct, we can say that it is an advantage, but it doesn't actually produce harmful gases. So that is incorrect. Variable supply, well, that is actually not an advantage. No harmful gases released is actually an advantage. And variable supply means that yes, it's not necessary that it will always give you a fixed amount of energy, right? So I think C is going to be the correct answer. So we are going to mark C, and let's move to the next one. The three situations are listed. Someone blowing air into a party balloon, a crane lifting a block of concrete, a pile of books rest on a shelf. In which situation work is done? Now this is very important, and we can actually now easily answer this question because we have completed work done. Now for work, two things are very important. That force must act on the body and the body must do work in the direction of force, right? So if someone is blowing air into a party balloon, the party balloon is obviously getting, it's getting big, so the force with which you are blowing air, right? So the force of blowing air, or I can just simply write work done in blowing air inside the party balloon is getting converted into the elastic potential energy as it is changing its shape. Is that correct? Right? If you're going to actually release the nozzle of the balloon, the all of the air will come out and it will come back to its original shape. A crane lifting a block of concrete. So again, a crane is lifting a block of concrete. That means that there's going to be work because the work done in lifting a concrete is getting converted into gravitational potential energy. A pile of books at rest on a shelf, it's not displacing, so there is no work done. So it's 1 and 2 only. That is option B. Moving on, a ball is falling towards the ground. Which transfer between energy stores is taking place? Now you can see that the questions that usually comes from this chapter are going to be very, very simple. So that if a ball is falling down, so at this point, now how we actually how we are going to look at this problem? We are going to say that this is actually a reference line for us. Now at the reference line, we actually assume that the gravitational potential energy of this line is 0. So the difference between these 2 points is going to be of mgh. That means this one has got mgh energy more than this reference line, right? So it's not like mgh is the absolute potential energy of any point. That statement is going to be wrong. This mgh is just the, what we can call, it is the potential energy relative to this reference line, or we can call this as ground. Now when it is going to fall, it will be under free fall, that is it will be under gravity. So acceleration will act on it, that is g, in the downward direction. That will actually accelerate it, and the speed of this ball will increase. And when it is going to strike the ground, it will be in motion. That means the potential energy will get converted into kinetic energy. So kinetic energy, so gravitational potential energy to kinetic energy is going to be the correct answer, right? And it will strike with certain speed, let's say v dash. Moving on to the fourth one, a pump does 460,000 joule of work to raise water to fill a tank. It takes 7 minutes to fill the tank. What is the power of the pump? I have already told you, although we missed to actually write the formula for power, but we'll do it now. Power was actually rate at which work is done. That means del W by del T. So the work done is 460,000 joules divided by 7 minutes. We have to write everything in SI units. So this is going to be 7 minutes is going to be converted into seconds, right? So this is going to be actually 46,000 divided by 42, and the answer is going to be in watt. And if you want to convert it into kilowatt, because I can see lots of answers in all of the answers are in kilowatt, what I'm going to do is, we know that 1 kilowatt can be written as 1000 watts. So that means let's divide this number by 1000. So you're going to get 46 by 42, and I don't even have to use calculator because it is slightly greater than 1, which has, I've got only one option, that is option A. So it's going to be 1.1 kilowatt. Moving on to the next one. How an object of mass m falls from a higher shelf to a lower shelf, how much gravitational potential energy does the object lose? Now you can actually sense that mainly these types of questions only come in your exams, right? So again, I'm going to discuss that. Let's say this is the reference line. So this one has got zero potential energy. So this one has got a potential energy of mgh1. So let's say this is gravitational potential energy P1. This one has got gravitational potential energy of mgh2. So the loss in gravitational potential energy is mgh1 minus mgh2. That loss is always written as initial minus final. So that means this is nothing but mg times h1 minus h2. So h1 minus h2 is mg in h1 minus h2 is option D. Moving on to the next one. Hopefully everything's clear till here. A box is initially at rest on the top of a rough surface. The box slides down the slope. The weight of the box is 20 Newton. The slope is 4 meter long. The box does 10 joule of work against the friction. Now, what do you really mean by work done against the friction? Work done against the friction, by this we mean to say that if you have got a box over here, something like this, and it is sliding down, so it is sliding down. So on this block, the friction force is acting somewhat in this direction, in the backward direction. So if work done against the friction is actually 10 joules, right? It's 10 joules. So now we are going to say that this work done. Now please understand how we are going to solve this problem. Work done by friction is 10 joules, and over here it has also gravitational potential energy. So this was the initial store. This was the initial store. And finally it will have over here, all the energy that will be left will be in the kinetic store. So how I see these types of problem is that let's suppose that you have got like, let's suppose you have got $1,000 in your pocket. Okay, quite a big amount. Let's suppose that you have got $100 in your pocket, right? And if you've got $100 in your pocket, now you're going to, let's suppose you're going to a market and you're spending your $100. So you're spending in two things. One is work done by friction, which is actually your commuting cost. And the another thing is when you're going to reach to a mall, or you're going to reach to your destination, you're going to probably you're going to buy something. So that is your kinetic store. So I'm going to write now, this is actually the conservation of energy. We are going to say that initially we only had gravitational potential energy, and the gravitational potential energy got spent into two things, that is work done by friction plus the left out energy is in the kinetic store. So gravitational potential energy is the mass of the body was, the weight of the body was 20 Newton. So I'm just going to write 20 because the gravitational potential energy is mgh and mg is weight. So they have already told us what mg is. So 20 times the height was 2 meters. 20 times 2 equals to work done by friction is 10 plus half. Now what I'm going to do is, if let's say if we want to find out the speed over here, so now what I'm going to do is I'm going to actually say that let's write it as instead of writing mass, I'm going to write it as 20 divided by 9.8 times v square, right? So this is going to become, this is going to be 30. Hopefully you're getting it. This is actually 40 minus 10 is 30. 1 by 2, 29.8 times v square. You can cancel out these zeros. You can do it by your way. So v square is going to be 9.8 times 3, and we can obviously use our calculator to find this because calculator is going to be allowed in these papers. So 9.8 times 3 is going to be 29.4. So this is going to be a little greater than 5. So that's 5.4. So 5.4 meter per second is your answer. So V is coming out to be, hopefully you can see this over here, V is coming out to be 5.4 meter per second. So now let's move to another question. So this question was actually good. Moving to another one, a microwave oven is rated at 500 watts. What do you really mean by rated at 500 watts? When you see something written like rated at, this means that when this microwave was manufactured at a factory, it was manufactured in such a way that it will consume 900 joules of energy in 1 second if it will get the sufficient amount of voltage that it requires, right? So 900 joules in 1 second it is going to consume. So 900 joules are transferred in every second is going to be absolutely correct. 900 amperes, 900 volt, 900 ohms doesn't make any sense, right? A option is absolutely correct. Moving on, a woman of mass 50 kg has 81 joule of kinetic energy. What is her speed? So we know that kinetic energy is nothing but half mv square. That means half times mass times the square of speed. Now kinetic energy is 81, mass is 50 kg, everything is an SI unit, times v square. So this is going to be 25. So v square is going to be 81 over 25. You can find it out using your calculator, although v is going to be 9 over 5. That will be again a little. Is everything fine over here? Hope so. Yes, everything's fine. So this is going to be just a little less than 2. Hopefully this is going to be nothing but 1.8, but let me check it. So 9 divided by 5 is just 1.8, right? This is going to be 1.8 meter per second. Option C. Moving on. Question 9 says the diagram shows the energy store of for a mobile cell phone and how the energy is transferred between the stores. What describes how the chemical energy is transferred? So this is for a mobile phone, right? So chemical energy will be transferred into electrical energy because that's what a battery is for, right? So it will be transferred into electrical work done and then so on. So now this is very important. By the way, this is sound. Having said that, let's move to the last one. A wind turbine is sorry is 30% efficient and an output of 2.5 megawatt. So now for finding out the efficiency, we are going to just write efficiency is power output. Now we wrote it for energy, but you can also write it for power. We wrote it something like this, that output power divided by input power into 100%. Just divided by time, it will get converted into power. So power output divided by power input multiplied by 100%. So efficiency is 30%. 30% basically means 30% basically is going to be, we are going to just write 30 over here. So P naught is going to be output power is 2.5 megawatt divided by Pi. That's what we need to find out, times 100. So Pi will be 250 divided by 30. That's around 8.3 megawatt. That's the correct answer, right? Having said that, let's now end this class because we have completed almost every topic of this chapter and we have also discussed some of the past year problems. If you have any doubt regarding this chapter, please write down your comment section. Please write down your doubt in the comment section. We'll get back to you and we'll try to rectify your doubt, right? Till we are going to come back with another video soon. Till then, take care. Thanks so much. Bye bye.